Hello everyone, Assalamu alaikum and good morning and good afternoon to the regions that you have joined from. Before we begin, if you can all please confirm that you can hear me and see the slide clearly by just putting yes in the chat window so that I'm able to great. Okay. Also, please feel free to introduce yourself, your name, your positions, and the company you belong to. It's really good to see an international audience of people from all the industries and backgrounds. Hello, hi, nice to meet you all. Okay, great. I welcome you all to today's webinar, which is on the implementation of ASME B31.8S API 1160 based PIMS software for cross-country pipeline. My name is Sayyida Samia Aves, and I am the lead software engineer at Velocity. For the next 2 hours, it will be our pleasure to host this webinar with you. So as you know that we are already hosting these webinars for quite some time, and this is our 62nd webinar in a series of technical webinars that we are conducting. As a practice, we are now conducting 1 webinar every month. You can follow us on LinkedIn and make sure to check our website to stay tuned to the latest updates. Also, all these webinars that we are conducting, they will be uploaded on our Velocity YouTube channel. So you can subscribe to our YouTube channel and stay connected with us. So today we have quite an experienced panel of speakers. I am with my colleagues, Mr. Ijazul Kareem Rao, Mr. Managing Director, Principal Integrity and Safety Consultant, Mr. Anthony James Williams, General Manager, Global Sales, Mr. Ali Arsalan, he is the head of our BI department, and myself. During this webinar, we encourage you all to keep asking in questions to clear any kind of doubts. We would like your engagement on this topic. This will not only help you, but also many others who can usually have the same kind of doubts. You can type in your queries in the Q&A window. You will either receive a reply in the window or we'll answer it live. We'll try to answer as many questions as possible during this session. Also, we'll be having a detailed question and answer sessions at the completion of this topic. Kindly accept our apologies if your question is not addressed. Due to the high volume of questions that we usually receive, in this given limited time, we have to be very selective. We'll also be issuing a participation certificate to all those who have attended at least 80% of the webinar and have participated in the discussions through Q&A sessions. Although it's a Sunday and most of us might be in the comfort of our homes, we should be aware of the emergency exits which are around us. In general, take care of ourselves and of those around us. We'll be touching key theoretical and practical aspects of the implementation of ASME B31.8S and API 1160. Today's agenda, it includes introduction about Velocity, the pipeline integrity overview, standards and regulations. We'll be sharing 1 case study overview, and we'll be presenting the software demo. We will be following a practical approach. We'll walk you through the key steps through the case study. Please note that the client name and the data have been redacted. So now I'll be handing it over to Mr. Ijazul Kareem Rao, who will be proceeding with today's topic.
Thank you, Ms. Samia. And Assalamu alaikum, everyone. Good day. Today's topic is PIMS, which is mainly will be focusing on PIMS onshore. The main reference standard would be ASME B31.8S, which is more or less comparable with the API 1160, both oil and gas pipelines. Before we go to topic, what is asset integrity? In general industrial definition point of view, AI is a continuous process of knowledge and experience applied throughout the life cycle of asset to manage the risk of failure and events in design, construction, during operation of the facilities, and till retirement or decommissioning. Now, if we define design integrity, then technical integrity, then operational integrity. Design integrity means like assets are designed in accordance with international standards or governing codes and standards of the local regulatory authorities. Then technical integrity means if appropriate processes like inspection, maintenance, HSC, integrity, or other associated departments are established, their role and responsibilities are established, and then how various assets like pressurized equipments, pipelines, electrical systems, instrumentation and control systems, and structural and civil and other assets are being managed during the operation phase of the assets by the processes. Then operational integrity means what the role of operation department, how they are operating the plant, whether they are following the operating manuals properly, and the procedures are in place, the KPIs are in place, alarm management system is in place, and operator-driven reliability is also in place. So basic objective is to keep running and within the IOWs, integrity operating windows of the plant limits. Now, overview of the plant, like a pipeline integrity system. A pipeline is a one, you can say tag, one equipment, what you say, but it may go kilometers and kilometers from one country to other country in terms of gas pipelines or oil pipelines, and then within the facilities. So pipeline integrity assessment is a process to evaluate the physical characteristics and safe operating conditions of a buried subsea pipeline with respect to applicable standards or code of practice. Since the environment around the pipeline is dynamic, pipeline integrity assessment needs to be a multi-phase process in response to the large number of variables involved. This implies that no single action or technique will be sufficient and that complementary actions are needed in order to ensure adequate overlap. Now, under pipeline integrity, there's a macro analysis and there could be a micro analysis as well. So, like in general terms, what we need to analyze, like historical data of the pipeline or the how the pipeline was designed and then procured and then built. So it will require, for example, diameter of the pipeline, wall thicknesses, grade of the steel, then type of big pipeline like a seamless, ERW, DSAW, class location, then year of installation, types of coatings, then operating pressures and temperatures, hydrotest data, inline inspection data, or DCVG, SIP surveys. In case of offshore pipelines, there could be like on-bottom stability, ROV inspections, and for example, the free spans, condition of the anodes, those things are also required as a part of macro analysis. And then in onshore pipeline or offshore pipeline, analyzing the existing CP systems capability, like what the life of a node, whether enough protection is being provided by the CP system. Then it is like IP type CP systems, year of permanent system installation type of system, like whether galvanic impressed current, analyze the trend in rectifier outputs with time, analyze pipe to soil potential at test stations, analyze previous pipeline survey data, identify areas where potential anomalies exist. Then in microanalysis, for example, wall thickness and flow detections like damage mechanisms, and this is not only by ILI, which is inline inspection by pigging, or it could be depth measurements as well, and there could be indirect surveys like conduct close interval SIP surveys or SIS surveys, then use proper survey procedure, use correct interruption ratio, interpret data and identify anomalies, then identify areas for additional surveys wherever it could be required, then conduct detailed surveys at selected locations from CIS, which could be DC voltage gradient, DCVG, then pipeline current mapping, electromagnetic surveys, soil resistivity surveys, then plan excavations and remedial actions if required. Basically, if you want to see the actual condition of the pipeline, and that will help you to dig the proper like holes where you can get the line empty and you can do required inspections. And in this process, you try to get the information like soil classification, soil texture, drainage characteristics, then topography of the area. Then how to analyze, for example, historical data, where like, so now there are various kind of like threats. There are 22 threats as per ASME B31.8S. Some threats are, first thing is starting with unknown. It is always there is a few things which would be unknown causes point of view. Then there are threats which are time dependent. There are threats which are not time dependent. Like external corrosion, internal corrosion, stress screen cracking are mostly called as time dependent. And then there are issues like resident or dormant kind of issues, manufacturing, fabrication related defects are there. Then equipment which are attached with the piping system, their gaskets, flanges, seals of the pumps may also have a problem. Then there are also random or time independent defects are there. For example, third party mechanical damage, like there could be a terrorism, there could be like any other issue which is caused by third party lines also. Then incorrect operational procedures could be one of the cause for the failures. Then weather related and outside force, for example, the excessive hot or cold weather, high wind, then hydrotechnical water related threats, including but not limited to the liquefaction, flooding, then channeling, scoring, and erosion related issues. Then geotechnical earth movement, like basically what you called earthquakes and soil settlements or land what you call falling down, or the mountain areas, there are land movements are also there. Then lightning due to weather, that will also be an issue. Regulations and industry standards. There are many standards are involved, but mainly the two standards which are basically a framework to manage integrity of the pipelines, both oil and gas, where ASME B31.8S is related to managing system integrity of gas pipelines, whereas API RP 1160 managing system integrity of hazardous liquid pipelines. When we compare the content of both standards, those are more or less same. There are some differences are there, but 80–90% they're matching with each other. Then other standards other than the design one, which is related to integrity, are mainly NACE, like ECDA, ICDA, and then, for example, stress screen cracking related direct assessment, which is NACE RP 204. Then control of external corrosion on underground or submerged piping system, which is SP 0169, and SP 0106, which is control of internal corrosion in steel pipeline and piping systems. Since the piping systems or pipeline are also having the valve station or compression stations or pumping stations, so up to a certain extent we may also need to refer API 510, 570. If there are bottles are there to collection of, for example, condensate, then 510 would also be applicable. Otherwise, 570, 571, API 580, API 581, API 579. Then API 1163, which is inline inspection system qualification standard. Then API RP 14E, which is related to sizing. Then ASME B31.4 and ASME B31.8, which are used for the design of liquid pipelines and gas pipelines, respectively. So, since our main topic is today the PIMS, Pipeline Integrity Management System, and which is being driven by mainly ASME B31.8S, Velocity has developed its PIMS system, which is also certified in compliance with this standard by third party. So, if we see the title, the subject, like people may get familiar with this standard, because in the today's presentation, many people are attending, but background point of view, they are ranging from young engineer from the university to the experienced people. So few things are very basics one, and then there would be some advanced things also would be discussed during today's session. Now, this is basically the title, and if we see the index point of view, so here, like number one, introduction, then integrity management program overview, then consequences, like how to establish consequences of any failure, then gathering, reviewing, and integrating data. Remember, pipelines are in kilometers, and there is a proper system is required how that information can be organized. Then risk assessment, then integrity assessment, then responses to integrity assessment and mitigation, repair and prevention, then integrity management plan, then performance plans, then communication plans, management of change plans, then quality control, terms and definitions. These are the contents basically of the standard, and then like other details are also there. It's quite easy to follow standard, and if we will be paying some attention and some time on this standard. So before we go in detail of the standard, there are a few definitions or abbreviations here. Like CP mean cathodic protection, CIS mean closed interval survey, DCVG mean direct current voltage gradient, DSAW pipe mean double submerged arc welded pipe, ERW pipe is electric resistance welded pipe, GIS is geographical information system, GPS is global positioning system, IL is inline inspection, MFL is magnetic flux leakage, MPI magnetic particle inspections, MAOP is maximal oil operating pressure, MIC is microbiologically influenced corrosion, entity mean non-destructive testing, PNID mean piping and instrumentation diagram, ROW mean right of the way of the pipelines, where the pipelines are passing in the field. SMYS is specified maximum minimum yield strength as per ASME standard. SCC is stress corrosion crack. Then few definitions like active corrosion mean corrosion that is continuing or not prevented or not arrested. The anomaly and pipeline data analysis mean the process through which anomaly and pipeline data are integrated and analyzed to further classify and characterize anomalies. Bell hole is execution that to minimize surface disturbance, like a bell hole, like making one who digging the area around the pipeline in certain 2 meter, 3 meter, so as we can see the pipeline, underground pipeline. Then caliper tool or geometry tool or instrumented inline inspection tool designed to record conditions such as dent, wrinkles, ovality, bend radius, and angle by sensing the shape of the internal surface of the pipe. Coating system is a complete number and type of coat applied to a substrate in to prevent the external corrosion of the pipeline. Components and pipeline component means an individual item or element fitted in the pipeline, like there could be valves, there could be flanges, there could be elbows, T's, and other closures. Then composite repair sleeves. These are the sleeves which are used to repair the pipeline in a certain condition. Then corrosion mean is a deterioration of a material, usually a metal, that results from an electrochemical reaction with its environment. Then corrosion inhibitor, a chemical which is injected in the pipeline to prevent corrosion. Corrosion rate mean the rate of corrosion which is taking place in the pipeline, any segment per year basis. Crack, a very narrow elongated defect caused by mechanical splitting into two parts. Dent, permanent deformation of the circular cross section of the pipe that produces a decrease in the diameter and in the concave inwards. Engineering assessment mean the engineering studies. Engineering critical assessment is engineering where we try to identify the criticality of the component of the pipe in terms of probability, consequence, and then see how critical is that particular segment. Inline inspection tool, there are basically pigging tools which are used like MFL or UT type tools that will be covering a little bit further. In-service pipelines mean the pipelines which are transporting the products in operating conditions. Pig launchers are where the pigs are basically launched or sent in the pipeline. Management of change mean the process in which changes are controlled in the pipeline or in any system. Mitigation mean the actions which are taken to prevent any defect or anomaly which may propagate. Performance-based integrity management program means like how to check the KPIs and performance of the pipeline and then required action to be taken. Pigging is basically ILI or a cleaning pigging is also there. So both types are called pigging. Pipe to soil potential is electrical potential difference between the surface of a buried or submerged metallic structure. The right of the way is the pipeline's route, and sometimes they are fenced, and sometimes there is some road or access is also provided. The survey could be made for the cross-country pipelines. Risk means measure of potential loss in terms of both the incident probability, likelihood of occurrence, and the magnitude of the consequences is multiple of both POF and COF. Then subject matter experts are basically experts, people who have a thorough knowledge about the subject. Third party damage mean basically third party other than the operator, if any party may play some role in the affecting the performance of the pipeline. The scope of the standard is basically to develop the standard, to develop the system so as you can manage the integrity of the pipeline system with global picture in mind. Purpose basically explained earlier. If you see that comprehensive, systematic, and integrated integrity management program provides the means to improve the safety of pipeline system. The use of this code is a supplement to the ASME B31.8 code, will allow pipeline operator to move closer to the goal. Such an integrity management program provides the information for an operator to effectively allocate resources for appropriate prevention, detection, and mitigation activities that will result in improved safety and minimize the number of incidents. So, principal point of view, like a set of principles is the basis for the intent and specific detail of this code, which is called like a functional requirement, system integrity, and integrity management program, and information integration. See, under functional requirement for integrity management shall be an engineered into new pipeline system from initial planning, design, material selection, construction. Integrity management of a pipeline starts with sound design, material selection, and construction of the pipeline in accordance with the applicable codes and good quality standards. System integrity requires commitment by all operating personnel using comprehensive, systematic, and integrated process to safely operate and maintain pipeline system. An integrity management program is continually evolving and must be flexible. An integrity management program should be customized to meet each operator's unique conditions. Information integration is a key component for managing system integrity. A key element of the integrity management framework is the integration of all pertinent information when performing risk assessment or condition assessment or integrity assessment. So risk assessment, I already explained, there's a POF and COF. Then performance measurement is defining the KPIs and then checking that like all integrity KPIs are properly defined, whether those are in terms of remnant life, or in terms of leakage, or any anomalies, or a positive KPIs could also be there, and then those are monitored by a proper system and reported. So if you see integrity management program overview, as per ASME B31.8S, there are 5 sub-elements. First thing is integrity management plan, then performance plan, then communication plan, management of change plan, quality control plan. So these all aspects are required to be reviewed and implemented in a proper sense and with a competent people under competent authority. Now, if you see that, like the step point of view, if you say gathering and reviewing and integrating the data, this is the first thing. So that's why we recommend always there should be either maybe Excel-based system or the new web-based systems or softwares which should be available to gather all the information and arrange in a way people can use at the time of need. Then review assumptions used in the risk assessment. Then there are not only steps, but this is as per the standard I'm referring. As we go detail, we'll also share the case study how we implement it. It's not so simple as seen here. Review assumption used in risk assessment. Then is risk assessment due to warranted based on review of assumptions? Then risk assessment is done. All threats evaluated. Then integrity assessment. Then response to integrity assessment and mitigations what are required. And then you identify a potential pipeline impact threat and try to manage. So this case, this code detailed two approaches to integrity management, which is prescriptive method and a performance-based method. Prescriptive method means require the least amount of data and analysis and can be successfully implemented by following the steps provided in this code. Incorporates expected worst case indications grow to establish interval between successive integrity assessments in exchange of reduced data requirement and less extensive analysis. Then performance-based, they require more knowledge of pipeline and consequently more data intensive risk assessment and analysis can be completed. The resulting performance-based integrity management program can contain more options for inspection intervals, inspection tools, mitigations, and preventive methods. The result of this performance-based method must meet and or exceed the result of the prescriptive methods. A performance-based program cannot be implemented until the operator has performed adequate integrity assessment that provide the data for performance-based program. Performance-based program further shall include the following integrity management parts: a description of the risk analysis and method employed, documentation of all the applicable data for each segment and where it was obtained, a documented analysis for determining integrity assessment intervals and mitigation repair methods, which include repairs and prevention, a documented performance metrics that in time will confirm the performance based options chosen by the operator. There is no single best approach that applicable to all pipeline systems. This is a caveat or a warning. But like both things, sometimes people say performance-based method mean reactive approach, but no, it is not calling for reactive approach. It is saying that once you have implemented a prescriptive-based or detailed system, then you can see the result of the assessment or behavior of the pipelines in terms of leaks, in terms of failures, in terms of the surprises you might be facing, or positive KPIs. Then accordingly, performance-based approach can be followed. And actions or efforts which are required to maintain a pipeline integrity management system could be reduced with the passage of time. So we will be having a question answer where please keep sending your questions, and as we'll be completing this section, we will be answering those questions. The first step in managing integrity is identifying potential threats to integrity. All threats to pipeline shall be considered. Gas pipeline incident data have been analyzed and classified by the pipeline research committee internal into 22 root causes or threats are identified. One of the cause reported by operator is unknown. That is no root cause or causes were identified. The remaining 21 threats are grouped into 9 categories of related failures, which are type of the I explained I think previous slide also. Go next. It is a repetition a little bit because this slide was in the beginning also. The total 22 root causes, one is unknown, then others are counted here. Time dependent, then manufacturing related defects, welding and fabrication related defects, equipments related defects, then random on time independent, there are third party, then incorrect operational procedures, weather related I covered earlier also. So now integrity management process. It is a more or less same as we covered earlier, but is a sort of repetition in the standard also. Gathering, reviewing, and integrity data, the review assumptions used in the risk assessment, and then is risk assessment due to warranted based on review of the assumptions, then risk assessment actual, all threats evaluated, integrity assessment also coming, and response to integrity assessment and mitigation. So risk assessment point of view or pipeline integrity point of view or threat based. So process is same, but only thing is you have to identify each threat separately. Then gathering and reviewing and integrating data. The first step in evaluating the potential threats for a pipeline system or segment is to define and gather the necessary data and information that characterize the segment and the potential threats to the segment. So we do first as a segmentation, we see implementation of this process as well in the next case study. So in this step, the operator performs the initial collection or review and integration of relevant data and information that are needed to understand the condition of pipe, identify the location specific threat to the integrity, and understand the public, environment, and operational consequences of the incident as well. The risk assessment, in this step, the data, basically these are the part, if you see that, we try to basic data, then identify the threat or identify damage mechanism or identify failure modes, and their probability is assessed. And then if something will go wrong, what could be the consequence in terms of basically safety, in terms of environment or health of the people. Then similarly, both POF and CF are multiplied and risk is calculated. This is the process of the risk assessment as I explained earlier. Then integrity assessment, basically integrity means there could be a defect, there could be growth of that particular defect, growth rate assessment, There could be fitness for service assessment in accordance with ASME B31G, or it could be as per API 579 standard. And then based on the risk assessment made in the previous step, the appropriate integrity assessments are selected and conducted. The integrity assessment methods are inline inspection, like measurements, the pressure testing, then or other integrity assessment methods. Integrity assessment method selection is based on the threats that are type of damage mechanisms or type of failure modes which are applicable. Then more than one integrity assessment methods may be required to address all the threats to a pipeline. Then under this assessment point of view, ECDA, ICDA, SCCDA, all those processes are also applicable. Then response to integrity assessment, mitigation, repair, like for example, once we have done integrity assessment, like we have conducted, like process point of view, we first identified the potential threats, then we carried out applicable inspections or assessments based on inspection results, and then now we know where are the weak areas, weak links, where is the potential defects, and where is the potential leakage, where we need to have some sort of repairs or some clamping, or maybe the repair of paint system. So practically, integrity assessment covers the complete inspection and assessment regime. And whether it is a DCVG, whether it's ILI, whether it is a SIP survey, then we follow the process of as per the NACE, ECDA, ICDA, SSCDA as well. So this is the process where main actions are required to be taken. After the data is established, after the segmentation of the pipelines are done, threats are identified, PF assigned, risk assigned, and then we go to the assessment part or inspection planning part. So once the results are known to us, then if there are defected areas or there are weak areas, if any mitigation action in terms of corrosion inhibition, in terms of repair, in terms of preventive clamping, those are done in this process. Update, integrate, and review data. So once you have basically done some corrective actions, some repairs, or some corrections, so that data has to be updated into the PIM system. That is one of the last part of the process. And so as you are ready for the next step. And once these corrections are done, you can reassess the risk. And if it's in the safe zone, then you can plan the next action for the next your integrity management campaign or inspection campaigns or plans what you want to execute in future. So based on like your integrity assessment or risk assessment, we try to prepare the integrity management plan for the coming years, next 10 years, 20 years. What actions are required to be done by the operator or the owner of the pipeline or inspection department of the pipeline or pipeline department itself, how your department is, or your company is organized. The integrity management plan is the outcome of applying the processes depicted in the integrity management process. The plan is documentation of execution of each of the steps and supporting analysis that are conducted. The plan shall include prevention, detection, like mitigation practices. The plan shall also have a schedule established that consider the timing of the practice deployed. The plan shall be periodically updated to reflect new information and current understanding of the integrity threats. Performance plans. Now, the operator shall collect performance information and periodically evaluate the success of its integrity assessment techniques, pipeline repair activities, and the mitigative risk control activities, whether those are working and effective. The operator shall also evaluate the effectiveness of its management system and processes in supporting sound integrity management decisions. The application of new technique into the integrity management program shall be evaluated for future use in the program. Communication plan. The operator shall develop and implement a plan for effective communication with all stakeholders, covering employees, the public, the emergency responders like district management, maybe like civil defense, the local officials, jurisdictional authorities, in order to keep the public informed about their integrity management efforts. The pipeline shall provide information. The plan shall provide information to be communicated to each stakeholder about the integrity plan and the results achieved. This is as per the local regulators, like specifically this American standard. So these guidelines are written in accordance with American working practices. Then management of change plan, if there is any change in the system or there is a change in the integrity management program as well, so it has to be properly documented. Pipeline system and environment in which they operate are seldom static. They will be changing. So for those changes, there would be a requirement of management of change program. A systematic process shall be used to ensure that prior to implementation, changes to the pipeline system design, operation, or maintenance are evaluated to their potential risk impacts, and to ensure that changes to the environment in which the pipeline operates are evaluated and risks are assessed, and there is no extra risk for the asset or to the people or to the environment. After these changes are made, they shall be incorporated as appropriate into the future risk assessment to ensure that the risk assessment process addresses the system as currently configured, operated, and maintained. The result of the plan mitigation plans mitigative activities should be used as a feedback for system and facilities design and operation. Quality control plan, for example, whatever activities which are being done, whether those are data gathering, whether it is risk assessment, whether it is integrity assessment, whether it is an inspection, or whether information, or whether there is a basically management of change. The quality of the actions should be ensured properly, and so as there are proper documentation, competent people are doing, errors are being verified and reviewed and corrected. So the quality aspects has to be maintained in each step of the basically PIMS system. Consequences point of view. See, now I earlier discussed about the threats. On the consequences point of view, when we go to risk assessment, risk is a multiple of POF and COF. The consequences of any failure, for example, if a pipeline is passing by any residential area and if it leaks, there could be basically effects on the environment, there could be effect on the people. If it catch fire, then it could be a huge impact on that particular area. In oil pipelines also, the oil pipelines, especially in third world countries, where the right of the way are not so protected and not basically like barricaded or fenced, people may go there with the intention of not knowing or maybe some stealing. So there are issues which can like leakage, fires, and there are casualties or fatalities. So consequence assessment point of view, like if wherever the pipeline would be passing, there are effects in terms of environment, in terms of fatality, in terms of health. So those has to be assessed, and it has to be basically multiplied by the probability of failure, and risk has to be assessed. So risk is a mathematical product of likelihood and consequence of event that result from a failure. Risk may be decreased by reducing either the likelihood or the consequence of a failure or both. This section specifically addresses the consequences portion of the risk equation. The operator shall consider consequences of potential of failure when prioritizing inspections and mitigation activities. The ASME B31.8 code manage risk to pipeline integrity by adjusting design and safety factors and inspections and maintenance frequencies as the potential consequence of a failure increase. This has done on an basically empirical basis without quantifying the consequence of a failure. So like there's safety class which is being applied, like the allowable stress or value which is being used in a residential area is quite low as compared to the allowable stress being used in the desert or the unmanned areas. The potential impact area, for example, if a pipeline may leak or fail, what could be the area where the pipeline would be affecting? This equation R is equal to 0.69 D over P under root. So US customary units and SI units, both equations are available, and it can tell how much area would be impacted by the pipeline. Then, for example, although this above one is for the natural gas, for other equations are required to be used. Although a similar methodology may be used for other lighter than air flammable gases. The natural gas factor of 0.69 is in the typical gas formula must be derived from the actual gas composition or range of composition being transported. Depending on the gas composition, the factor may be significantly higher or lower than this number. The methodology may not be applicable or sufficient for non-flammable gases, toxic gases, and others. However, like nowadays, see, consequence modeling can also be done by the other software like DNV's FAST, which is very good for dispersion modeling, and it got the capability to model whatever the chemicals or hydrocarbons are in the pipeline, and that can also be used. So then other considerations, as I said, that can also be used, and this equation is also available for consequence assessments. In RBI of the pipelines, we normally take the help from the QRA data. The basis of the information is the QRA data, like which can be used for the consequence or area which would be affected in terms of any leak or of a hydrocarbon or toxic element of that gas pipeline. Then ranking of potential impacts areas, like it is a pipeline passing by, then this is basically a circle how the R would be affecting, and this is a school or area if it's coming in that particular point. So that the decision to be taken, like whether school could be allowed to be built within the vicinity of that consequence area or not. Generally, they're moved away from the effective area of the pipeline. So basically, factor to consider when evaluating the consequence of failure within the impact zone, the operator shall consider at least the following: the number and location of inhabited structures, proximity of the population to the pipeline, including a consideration of man-made or natural barriers that may provide some level of protection, proximity of population with limited or impaired mobility, for example, hospitals, schools, childcare center, retirement facilities, prison, recreation area, particularly in the unprotected outside areas should be considered. Then property damage, environment damage, effect of unignited gas releases, security or liability of gas supply, then public convenience and necessity, the potential for secondary failures, duration of a failure event, including the product depreciation and the potential fire. Then gathering review, like now we are going into the more details, like how to gather the information. So I'm spending more time on theoretical or narrating the standard. Mostly the contents are same, which are part of the ASME B31.8S, but the focus is to if you are getting familiar with the terminologies given in the ASME B31.8S, then we will be showing the worked example also, which is like quite simple as we create the practice. And at narrating the standard, it looks a little boring. I'm sorry, there's less chances to get people involved, but I hope some of them will not be sleeping. So please be active, and we will be going to the question answer session soon. But this is a little boring subject, but it is interesting for the sake of knowledge. Gathering, reviewing, and integrating data. So the things which I discussed earlier, like now we're going more details on the same things. This section provides a systematic process for pipeline operator to collect and effectively utilize the data elements necessary for risk assessment or integrity assessment or any kind of decision making for the pipeline. Comprehensive pipeline facility knowledge is an essential component of the performance-based integrity management program. Information and operational history, the environment around the pipeline, mitigation techniques employed, and process procedure review is also necessary. Data are a key element in the decision-making process and required for program implementation. Data requirements. The operator shall have a comprehensive plan for collecting all data sets. The operator must first collect. Operator means the consultant or engineers who are working on the facility, on the pipeline. The data required to perform risk assessment. Implementation of the integrity management program will drive the collection and prioritization of additional data elements required to move, fully understand, and prevent mitigation the threats. Then Prescriptive integrity management program, like attributes of the data, like what data is normally required in the PIMS system, like pipeline, wall thickness, diameter, seam type, manufacturer data, material properties, then equipment properties, then construction point of information, like year of installation, bending method, joining method, process and inspection results, like RT results or BAUT results, depth of cover, crossings, then pressure test, field coating methods, soil, backfill, then inspection reports, cathodic protection installed, coating type, then operational like gas quality, flow rate, leak or failure history, coating condition, CP system performance, pipe wall thickness, pipe inspection reports, ODID of the corrosion monitoring, pressure fluctuations, regulator or relief performance, encroachments by third party, then repairs, if any terrorism, vandalism, or external forces, then inspection, for example, pressure test, inline inspections, geometry tool inspection, bell hole inspections, CP inspections, coating audits. So these all informations are required to be gathered basically as a pipeline, basic information in the PIMS system. Then, like there's also there is no standard list for for performance based, but if we see it whatever the KPI, let's say we wish to have a zero leak. So your information management system could be based on that. Like operator says, whatever it takes, we'll take all the precautionary or preventive measures so that there is no leakage. And if that is the performance criteria, then accordingly all information has to be gathered and arranged for the PIM system so as that target of the performance criteria could be met. The quantity and specific data elements will vary between operators within a given pipeline system. Focus shall be on collecting the data necessary to evaluate areas of concern and other specific areas of high risk. These data are then integrated into the initial data. The volume and type of data will expand as the plan implemented over years of operation. Data sources. Like data sources point of view, if we see, the first thing should be the pipeline specification. Then if there are P&IDs, alignment sheets, then coating specification, CP specification. All the engineering data is the first, hydraulic calculations, corrosion inhibition details. So then the pipeline GIS system, and like a route point of view, ROV data, soil resistivity data. There are a lot of information which is required as a part of information, and these details are available through the engineering document first. Then survey of the all applied locations, for example, when inspections or surveys are being conducted. Then existing management information system, geographical information, like if we have a route of the pipeline, gradient known, and if some failures, the root cause analysis is done and that data is also available. Then other environmental data point of view, we can take information from the local regulators and other databases, like if the like we need to have information about the district authorities or civil defense or other regulators, that information is also available. Then research organization may also provide some data, industry consortiums and other information can be planned as well. So data collection, review and analysis. See, this is the basic thing when a pipeline integrity management system is being established. So how to collate the information, how to arrange the information, how to use that information. So the pipeline management system or software basically are there various softwares are available. Whale plant PIM system is one of those, and these are like data. If I go back, attributes. Yes, data attributes are defined and data is gathered, whether it's the graphical form, whether it's attachments. So those all informations are required to be maintained in the system properly. The individual data elements shall be brought together and analyzed in their context to realize that full value of integrity management and risk assessment can be performed. A major strength of an effective integrity management program lies in the ability to merge and utilize the multiple data elements obtained from several sources to provide an improved confidence that a specific threat may or may not apply to a pipeline segment. It can also lead to an improved analysis of the overall risk. Data integration can also be accomplished manually or graphically or through a manual system. It's not compulsory there should be a software system, but it's easy nowadays to have a basically software database rather than a manual database. Data integration, manual integration, and graphical integration could go both side by side also. But whether manual integration or graphical integration, it is possible only through any software system rather than a paper-based system. Now, since both gas pipelines and oil pipelines are covered under PIMS system, so but if you see, ASME has issued only 11, basically ASME B31.8S, and API is released 1160. But if you go both standards, they are wrapped in each other. Both are American standards, and the elements of integrity management in both standards are more or less same. In next presentation, we will also make the matrix where all elements can be compared. In this presentation, I missed to make that basically compliance matrix between these two standards. But as per our working practice, both are more or less same. If you see, I will explain, like integrity management program, same terminology is there. Then high consequence area or consequence assessment. Then if you see data gathering and review and integration, same is in ASME. All these three terminologies, what you have seen now, are risk assessment, right? So these are the same as in the ASME B31.8S also. Then initial baseline assessment plan, development and implementation. That is also assessment or development of integrity assessment plan in the ASME B31.8S. Similarly, mitigation option with the repairs or basically repairs or I would say replacements. That's a part of the mitigation plans. Then revisions of the integrity management plan, which updation the plan based on the new information, new data, what you get. Then integrity management of pipeline, pump stations, and terminals. So this is the area, but ASME 31.8S is covering compression stations. They are saying pumping areas because pumps are applicable on the oil pipelines. Then programs of evaluation, the same details in some other name available under ASME B31.8S. Management of change is same. If you see the anomaly types, these are the threats or the failure of causes of the failure. Then repair strategies, they made appendix. This appendix is another term that's available there. Then standard data field for the tracking pipeline releases. Then standard data fields for pipelines like infrastructure information. This data management there also. So if you see, both standards are more or less same. If it does not matter whether you try to follow API 1160 or we try to follow ASME 31.8S, both are practically matching with each other. So this is basically the standard. I'm not passing the more details. Before we go to the case study, we'll take a question answer break now. Who will read the questions?
Here are some questions. Between short and long radius bend, which one has higher corrosion based on your field experience?
See, in general terms, short radius would have a more erosion corrosion chances, and that would have a more corrosion chances.
Okay, next question. Is there any relation between individual API new certification of API 1184 and pipeline integrity management webinar?
See, API 1184 or 784?
1184.
What's the title of that? I don't remember the title.
It's related to inspection.
See,
Pipeline facility construction inspection.
see, API 1160 or ASME B31.8S, they are covering basic element of the PIMS system. And whether there is engineering related data or inspection activities or a mitigation plan or integrity assessment plan. So they are very much supportive, basically standards for API, for PIM system. They're not different, they're supporting each other, they complement each other.
Okay, next question. How can cross-country be controlled directly by a remote control system?
No, there's no remote control can cover the PIM system. PIM system, a pipeline integrity management system is managed by the operators. There is their integrity department, There are patrols by the vehicle. There could be like a patrol by like driverless, like by drones to see the like if there is no third party coming in between. But drones can only be used for monitoring purpose. But mostly pipelines are underground, and drone will not be able to see other than the right of the way of the pipeline.
Next question. How to calculate ERF for pipeline?
See, there's a formula under ASME B31G
We can,
based on the defects.
we can write that formula and check.
Yes, that's available there, right? It may be some example, it would be there in the case study, but I'm not sure. That's defect assessment formula.
Next question. Why are you using pipelines on chlorine plant?
See again,
Why are you using pipelines on chlorine plant?
chlorine plant.
Yes.
Yes,
Chlorine.
chlorine plant.
See, pipeline is a component or equipment of the facility to transport pollutant from one area to other area. If chlorine or any chemical would be transported within the chemical chlorine plant, so pipelines would be required. Next question.
Next question. Does product of the pipeline put any impact on data?
Yes, because if the product is corrosive, there would be more integrity threats. If product would have some toxic element, it would have some consequences, aspects or effects on the surroundings.
Next question. Any sudden fluctuations in data will affect software and end results?
See, softwares are mostly steady state, and it does not go with the like a DCS or SCADA system point of view. But that like a DCS and SCADA information is available to show any fluctuation, sudden pressure drop, sudden shutdown, or a sudden surge situation in the pipeline. So those are the major information sources for the pipeline. But PIMS software may not be able to cover that part. Okay. So now, no further question now, and now we go through the case study. Then we'll also demonstrate our PIMS software in a brief demonstration, and so then we have a question answer session at the end of this session of the discussion as well. So scope of work, what we basically implemented for this particular client: development of pipeline integrity management system manual in line with ASME B31.8S. This was the one scope element. Then development of customized PIM software as per client requirements in line with ASME B31.8S. Comprehensive training and hands-on familiarization of client engineers and staff. So what we covered: equipment as a 400, and package equipment piping system 330 and total 730, piping system altogether 2500, and package item 3000 together 5500. So these are the equipments. And then onshore pipeline 2, diameters 48 inch, 30 inch, and 24 inch. Offshore pipeline 2, which is 30 and 24 inch diameter. The onshore pipeline length was 1410 kilometers, and offshore 215 kilometers. Following deliverable which are successfully delivered to the client: pipeline integrity management manual, then provision of an implementation wheel plant, a complete integration solution which covered PIMS, pipeline integrity management system, pressurized equipment management system, then EIRMS, electrical instrumentation and rotary management system. ISMS is a inspection scheduling management system. CPMS was also part of the deliverable. Preparation of 10 operating procedures for buried pipelines as per ASME B31.8S, which we covered: intelligent pigging using magnetic flux leakage tool, pressure test, hydro testing, then closed interval survey CIS, current voltage gradient surveys, ACVG and DCVG, pipeline current mapping, soil resistivity surveys, then CP monitoring procedure, coating and pipe service visual inspection procedure, soil analysis procedure, ICDA procedure. Approach point of view, the same as per the ASME B31.8S. So we have gone to these steps. For example, pipeline data first, which covered pipeline description, basic data, operational data, profile of the pipeline, and pipeline layout. Then it was inspection history survey records, which all were logged in, and then as a part of it, pipeline assessment and a pipeline section identification. We allocated damage mechanisms for each section, then identification of POF and COF for each damage mechanism, risk assessment, Then condition summary, inspection plans were prepared. So the same defects and RBI assessment was done. If there's no defect, then it's go to straight away to the defect assessment. If defects, then the defect and RBI assessment. Then under RBI, there is a metal loss and threat assessment, defect assessment, inspection results based on this. Condition assessment is corrosion coupons, direct examination of the pipeline results. Then condition monitoring by visual inspection, leak failures, replacement, fluid analysis, weight loss coupons, ERP results or header test results. Then pipeline assessment of the same pattern we have done as we do normal RBI process. So pipeline integrity assessment for new pipeline, for example, development and of asset mechanical data register, then pipeline section identification, allocation of damage mechanisms for each or threats for each section of the pipeline, identification of POF and COF factors, risk assessment, condition summary, inspection plans, development basically. Then pipeline data point of view, the list of document data required for the pipeline integrity management. Basically, see, this was the point what we were discussing earlier, like what are the sources of information of the data when you are developing basically PIMS system. So piping and instrumentation diagram, process flow diagram, then pipeline layout drawing, engineering data, then process data, design changes report, operations, maintenance and repair data, chemical injection type and injection point data, as-built drawings, operation and maintenance procedures, emergency response procedures, then GIS coordinates and pipeline inspection data, for example, existing CP monitoring results, close interval potential data, intelligent pigging and ILI inspection results, then coating assessment survey data, visual and UT gauging data, initial assessment of pipelines, then component assessment data, third-party damage-related data. So all these data is gathered and basically assembled in the PIM system well plant. So this is like a screenshot of the pipeline dashboard hierarchy, like how many pipelines will go into the high risk or the low risk. So here, if you see two pipelines which are remnant life between 2 to 7 years, right? Here, like high risk is 1 and medium risk is 1. This is a half of divided because lines are divided. This data because to protect the basically the secrecy of the data, we have changed the information here. So we are not showing the actual case. Otherwise, it will reflect the information. So various client information has been mixed up. So you will not reach to the client. So please, this is for demonstration purpose. So as we can demonstrate as well as we can protect the secrecy of data of our client as well. So here this is the information where some basic information, pipeline description with system description, like system description, system boundaries, system interface, then system description, system design. So here if you see the information is divided into the basic data, operational data, profile, pipeline layout, and specific data. So next slide, going to the basic data. Under basic data, for each section of the pipeline, service, dimensions, position and positioning system, age, material, design, then corrosion protection, primary protection, secondary protection, isolation, cathodic protection features. Next is the operational data. Operational data means service, chemical injection, inspectability, temperature, pressure, all information. Then profile. Profile got a lot of details. For example, it's got pipeline route, then design data, location, safety class, diameter, wall thickness, corrosion allowance, fabrication tolerance, then pipeline material, SMYS, SMTS, steel density, steel E modulus, pipeline coating, operational data, temperature, pressure, and then the other data is also there. So the long list of information which need to be gathered for each meter of the pipeline, not kilometer. Then next is the, for example, sectioning pipeline layout. Then there are sections, various sections are there, and then it will divide it into like a 100 kilometer pipeline could be divided into 20, 30, or maybe around those sections where all crossings, all interfaces, and all areas are identified as the situation outside the pipeline would be changing. Remember, inside fluid would remain same, but outside pipeline data may change with passage of time. So this is the crossings, sections, component and crossings railway crossing, river crossing, road crossings. As we go, those we marked on the pipeline. So if you see that to have one pipeline, only the engineering related data, so it requires a lot of information, and it is practically difficult to show this information without having a proper software. So after crossing, the survey records, like the inspection history records. So there could be various inspections like DCVG, SIP survey, ILI, whatever inspection campaigns are run by the uh, operator inspection department. Those are required to be saved in the system. Like surveys, for example, there are, if you see the type of survey point of view, there will be ILI data, in direct assessment information, hydro test, or the ILI inline inspection data as well. Then metal loss, direct thickness, CP reading, anomaly, cracks. So all this information is required to be imported and required to be saved in the system before we go to the next step. So these are the basically DCVG data, indirect inspection results, and you can see this is the pipeline length going, and there's the variable of the data what you wish to see. Condition meeting data, for example, visual inspection, leak, failure, replacement, fluid analysis, weight loss coupon, ERP, and hydro tests. Bell hole data, if we are having any bell hole data, that information can be saved. Then subdividing the pipeline system into sections, like if you see this is the graphical, this drawing is made outside, like how the pipeline is divided into various sections. The risks are not uniform through the pipeline system, and partly due to the geography and geometry, partly because of changes in internal conditions, that fluid water near the production well or after a pump compressor station, and partly because it's unrelated threatening activity might be localized. So here we try to divide the pipeline into various sections where the damage mechanism, this terminology as per API 571, at various sections, various crossings are marked. It is a quite tedious activity, take quite effective man hours, which we need to spend, and then we can identify all the threats, and these are modeled in the PIM software. So if you go to assessment point of view, so all those threats, these are the sections of the pipeline, then we identify all the damage mechanism with internal, external, or threat, and each threat is assessed in the system. Like threats we already covered before, all threats are covered under this API, whale plant PIM system, whether onshore, offshore. So identification of damage mechanism, internal, external threats are covered by API 571 mainly, then 1160 or DNV RP 116, DNV F107, ASME. So these standards are covered, and our internal threats or damage mechanism, external threats or damage mechanisms are covered under the system, and they could be modeled, they could be assessed also. Then compliance with ICDA, compliance with ECDA, compliance with SSCDA, those are options who are basically done in accordance with, like ICDA was done as per SP, NACE SP-02 or 0206. Then compliance with SCCDA, which is done as per NACE RP 0204. And SCCDA, like the operating stress exceed, if the, like these are the conditions, 60% of the SMYS, the operating temperature has historically exceed 38 degrees Celsius. The segment is less than or equal to 32 kilometers. Then age of the pipeline is greater than or equal to 10 years. The coating type is other than fusion bonded epoxy. These are the conditions. And as per the client data, the age, basically this was practically considered not applicable. Like these were the threats which were applicable in this particular case, like internal 20, which is erosion corrosion as per the API 571 tag number. Then CO2 42, then under deposit 67. External 47, 58, 51, 68. Then in cracking point of view, these were considered like with no API 571 reference, but we have assessed all this. Then calculation of PFCF, this approach was used. As we explained earlier, risk is probability of failure and consequence of failure. The combination of two key factors, probability of failure and consequence of failure. Consequence are calculated based on the fluid properties, temperatures, pressures, and inventory. Probability is based on generic or average failure frequency data. And analysis is then performed considering important failure mechanisms for each pipeline section to determine if it is more or less likely to fail than average. Then corrosion rate assessment, basically we try to assess both short-term corrosion rate and long-term corrosion rates, which is basically long-term is T nominal minus T last measured. Thickness nominal, thickness last measured, then data divided by data measured thickness, sorry, date measured thickness and date of the service start. Then MCR, which is the short term, is the second last thickness and the last thickness, then date of last measured date inspection and date of the second last inspection. Then whereas like a long term and short term corrosion rate and CA is corrosion alarms. Development of inspection plan based on the basically the risk based on remnant life, we try to basically determine by following if like RPI inspection interval calculation empirical equation, and it will help to determine like what kind of inspection is required and what should be the next date. So this is basically a screenshot allocating damage mechanisms. So we have identified thinning, cracking, then third party and weather related, and with 42, 23 vandalism or floods. And then next stage would be the assessment. We're assigning the, basically the POF for against each damage mechanism. And there is also a model available to calculate the corrosion rate theoretical as well. Then this is the basically the corrosion calculation model, like base corrosion rate, total coating effectiveness. Like this is the soil corrosion. The model is available. And if we assess the calculation based on the soil corrosion 58, then like base corrosion rate, soil resistivity adjustment, total coating effectiveness factor, then cathodic protection effectiveness factor, then equipment temperature adjustment, then we calculate the corrosion rate based on this. The software will have a capability and it can do it. Then this is the well plant screen for risk assessment, consequences of potential impact area, like how much the impact area would be there based on the MAOP and radius. This is the calculation available in the ASME B31.8S. So this will we calculate the radius in feet and radius in meters, and as a under the consequence assessment. Is the consequence of failure like normal based on the business, the level 1, level 2, level 3 options available. This is the consequence assessment, health and safety point of view. It got fire, toxic, and explosion. Then it's a consequence assessment environment point of view. It got also 3 levels: location, surface of spill, the consequence class, environmental toxicity, and then gas emissions and so on. So at the end, for one particular section, it is showing the section 1 against each damage mechanism, what is the risk. So then it is a basically KP wise data. If you see there's the kilometers, and if you see there's a red, medium to high risk is high risk, and then there's a between low or medium high risk, yellow. And in this way, complete pipeline can be seen how the risk profile is. Then planning calculation, what should be the next inspection? It covers the metal loss, corrosion rate, remnant life, next inspection date, and then accordingly we can see what should be the next inspection, what the last inspection date. So this is an inspection plan. Basically, we want to make through CMS system, like what activities we wish to do with what interval, years, like 10-year one, 5-year one, 2 years one, whatever surveys we wish to do, those inspection plans are available. Defect assessment features available in the software, which is metal loss. Then the defect assessment, both options are available, and say working pressure calculation, the formula is available. And like as a result, we see that these are the curves of the 31G, and there was a question MAOP or ERF factor. So these factors are calculated in this model in the uncorroded pipe assessment and defect assessment. In the system, we have option to show, for example, code check, allocate damage group, historical trend, risk assessment, distribution of the defect on the orientation point of view, and then we can see external defect, clock orientation, defect versus profile also can be seen. So say working pressure point of view. So as MPOV is less than P, therefore the corroded region is acceptable E for that This is one of the result of this particular pipeline, what we are showing the result here. Then defect assessment results point of view, like if we have seen the metal loss, then corrosion rate, then remnant life, and then we can see with the pipeline, the life is coming quite high, but we should normally show more than 7 years or less than 7 years. But geographical distribution of the defects at the various defect data is there. Distribution of internal defect, percentage defects with depth versus KP, kilometer post, you can see this. And this is a normal like a defect depth in percentage point of view. The maximum defect size was 29.1%. So this sample PIMS report, one of the report, there are various reports options are available and can be generated by the system. Portfolio assessment risk by damage group, then pipeline integrity report, then inspection planning. So various reports are there, only 3 sample reports are shown here. We'll also have some live demonstration of the system after the demonstration of the slides. Then verification of mechanical design as per 31G at the worst corroded area. ASME B31G calculations were performed to calculate the safe working pressure, and 30-inch pipeline passed mechanical verification. You can see as per this line. If, for example, 0, 1 RLA 5 to 10 is 1, and RLA greater than 20 is 46. Basically, components were there in the pipe. This is the one weakest component. Here, there's a, if you see that pipeline integrity assessment result of 13-inch buried pipeline, risk analysis and integrity assessment of 13-inch pipeline was carried out by using Virplant software module, and summary result is there. For example, total section 29, high 0, medium high 7, medium 40, 0 low, and this is the result, right? And there are 7 sections. The 13-inch pipeline, 3 LPE layer polyethylene coated pipeline. In current operating scenario, pipeline is fit for service. The operating history revealed that during 2003 and 4, gas stream from injection point is found contaminated with black powder. Black powder erodes internals of valves, thus making these ineffective for isolation, and plugs the instruments as well, tubing. As per 2016 survey, overall coating condition at the pipeline is good. Coating disbondment were observed between the coating and pipeline service at few bell hole locations. No dents or crack-like defects were found at excavated locations. Internal and external metal loss was observed at various locations at excavated bell holes. Then corrosion rust was observed at a nearby girth weld joint of bell hole location number this. Sign of water dripping, seepage alongside pipeline coating at bell hole this were reported. At these locations, coating was found intact, bearing good adhesion, and no corrosion or pitting was observed at these locations. Maximum metal loss 7.37% has occurred at bell hole number this. So all this data is in the part of the system and can be summarized. Then there is recommendations that were given based on the result of integrity assessment of the pipeline. The following recommendations were given. CO2 and H2S can cause accelerated internal corrosion in the presence of moisture. It is therefore recommended that online chemical composition and moisture analyzers which are directly installed at custody transfer point shall be connected through RTU to client control room for online data monitoring, recording, including capturing any upset condition. It is also recommended to increase the frequency of cleaning by pigging at yearly basis instead of using cup big B1D1 pig shall be used. Pig speed shall be controlled from 0.5 to 1 meter per second to achieve good cleaning. It is recommended to frequently pig this line, initially every quarter, and then adjust pigging frequency depending on the amount of debris collected. Amount of collected debris in pig trap shall not be more than 1 to 2 kg. As client provide information, nominal wall thickness for 13-inch pipeline is 11.12 and minimum required thickness 10.02. This indicating that very minimal allowance is considered for pipeline structural integrity. Client is to review their selection of design pipe thickness based on API 574 for future pipeline constructions. So this is a velocity project report which we submitted. Content point of view, along with the PIM software. So here, if you see compliance with the 31.8S also applicable, identity threats are there, mechanical design verification is there, assessment of the indirect like surveys, selected bell holes, integrity assessment is done, then finding recommendations. So we have done the assessment as per ASME B31.8S and all criteria were met. Then the documents which are basically developed, the development of pipeline integrity management manual. Velocity prepared a pipeline integrity management manual in compliance with 31.8S. PIMS manual were prepared, and this is the content of the manual. For example, introduction, company PIMS policy and objectives, company organization structure, PIM organizational chart, then legal and code compliance requirement, pipeline integrity management program, which covers integrity management plans, then how to operate, inspection and maintenance changeover, then basically performance plans, communication plans. So all elements which are part of 31.8S or API 1160 are covered in this method. Then inspection procedures, what we prepared for the client, like ILI procedure, pressure testing, hydro testing procedure, close interval SIP survey procedure, then DCVG or ACVG procedures, pipe current mapping procedures, soil resistivity survey procedures, then CP monitoring procedures, coating and pipe surface visual inspection procedures, soil survey, soil analysis procedures, ICDA procedures, and like if we show that there are internal data assessment procedure, index point of view. So detailed procedure, pre-assessment, detailed examination, post-examination, record and documentation, and data required to use ICDA methodology, mathematically simplified flow modeling approach, and complete flow chart for ICDA. Similarly, other procedure pipeline current mapper. So this is the cover of the component, like index. Then last one is a CP monitoring test. Now we'll go to demonstration. My colleague, Mr. Arshad, is our head of software division. He would be demonstrating the software in 5-10 minutes, and then we'll take the question answer as a last. Thank you. Please bear with us. We have to change the screen of the software. Please bear with us. It's taking a few seconds.
Yes. Hello, everyone. So this is the dashboard of the main software well plant, which is a modular effort. So you can see different modules like the pressurized equipment, PMS, which is using for the piping and equipment, structure, offshore structure, which is called all your offshore structure, pipeline onshore, pipeline offshore, PSQMS, electrical equipment, wellhead in the civil inspection management system, cathodic protection, APMS, which is asset performance management system, CMS interface, like using this interface, you can interface with SAP, Oracle, Maxim, or any other third-party system. And then ISMS, inspection scheduling management system. So these are the modular approach for today. Our webinar, we are going for the PIMS onshore. So on the main screen, you will see the dashboard, which is showing count of different parameters, like the integrity parameters remaining live, less than 2, 2 to 7, greater than 7. Risk, based on the client, the risk matrix can be configured in the system, which will be showing you high, medium, low. Inspection PM activities, like how many pipeline planned for the current year, execute at the current year and overdue. The corrosion rate, which will be calculated by the software. Inspection work order and bed actor, like which is coming from the ERP system. So you can see the inspection work order and bed actor. And failure in replacement, like defect in current year, leaks in the current year, replacement in the current year. Then there are also some other parameters like KPI, quality change management of change, and some other information. So this is the dashboard view. You can go to the pipeline data, the form view, where you can see one line data at a time. On the left side, you can see the tree, like the company, then area, location area, and then you will see all your pipeline. So here is the main pipeline data, basic data with operational data like general composition, what is your product, what is composition inside that product, chemical injection, monitoring, maintenance, And then profile, so you can see all your profile data here based on the KP, what different KP you can see with the graphical representation. Pipeline layout, like the test post on your line, you can define all your test post sections. So each pipeline can be divided in multiple sections with the section name, section type, and some other information. Then the component, if there's any component you get load here. The crossing, all your crossing, road crossing, railway crossing, and other crossing you can see on your pipeline and anchor location. And then there is some specific data on the top, like you can new edit, delete data using one by one, or you have the bulk load feature and you can attach all the documents with this pipeline. Next is like the history and survey records. So all your survey information you can attach here. Once you have the survey, then you have go for the inspection data. So eye inspection, like the metal loss, direct thickness, here you will see your defect, length, width, and metal loss, all the information and in the graphical way. CP reading, anomaly crack, anomaly dents, and then the direct assessment, pipe to soil, DCVG survey. So all those information you can see in the graphical way and in the list view. Then the condition monitoring, like bellow hole examination, fluid analysis, corrosion coupon, and ERP. Next is like the defect assessment. So based on your ILI result, like IP survey or direct thickness results. So here you will see all your result. Further, you can filter with different parameter like defect length, depth, defect width, defect depth, and survey ID, and you can proceed for the detailed assessment, like metal loss assessment. So here, all the calculation will be done by the software based on the standard B31G modified like operating pressure, MOP, test pressure, B31G, and shell. So the failure pressure, factor of safety, P-safe, and ERF will calculate by the software. And here you will see all the defects based on the graphical representation, like if it is below the curve, so it is in the safe zone. If it is outside the curve, so then you need to do for the detailed assessment of those. Further, like I look at damage group, historical trend, risk assessment, and some other details are there. Next is the assessment results. So based on your selected corrosion rate, like Bayard, which has come from your history, estimated, which will be coming based on your ECR model or expect corrosion rate, you can calculate your remaining life and then inspection interval. Similar way, you have the dent assessment and the crack assessment. Next is the failure and replacement. So if there's any leak and failure on the system, you can record here, and any replacement that will be recorded here. Next is the pipeline assessment. So as we see in the pipeline data, we divide the pipeline in different sections. So all sections are available. Then next is allocate damage group. So for each section, we need to define the damage group like thinning, cracking, third party damage, and weather related. So all groups are available in the system like thinning, so whatever applicable mode, similar cracking, thermal fatigue, and other groups which is available in the system. Then velocity RBI. So for each section like thinning, if you have the Mayer corrosion rate, that will be considered for the calculation of probability assessment. Otherwise, the ECR model, which is available in the system, based on that you can calculate your corrosion rate, like this is 55 soil corrosion, and other model CO2 and whatever applicable that will be enabled, remaining will be disabled. Based on that, software will give you the ECR corrosion rate. Similar way there is for cracking models available inside the software. Then the consequence assessment. So economic, there is level 1, level 2, and level 3. Based on the available information, you can use the level. Similar for safety and environment. In the confidence assessment questionnaires, and then in condition summary, you can see the overall summary of your pipeline. So this is for one section. What is risk for each failure mode? Like this is for thinning, medium, for cracking, medium, third party damage, medium, high. And the section risk will be overall the high risk of all the damage mechanism, which is the medium high. And you can also see all the sections. Next is the risk assessment. Same information you can view in the graphical way and the chart view with the risk matrix. So this is the risk matrix. In the inspection plan calculation, so like the system will give you the last inspection, which is coming from your history. Next inspection, it will calculate by the software with the remaining life like 7.2 year, inspection plan factor, and inspection interval. Design life, life in service, treatment. So all these things will be calculated by software based on your selected corrosion rate. So there are multiple options like Mayer, estimated, expert, or corrosion coupon. If you have corrosion coupon, based on that, you can also calculate your remaining life. Then the integrity operating windows. So you can record all your operating windows here, and inspection plan. So in inspection plan, logistic requirement, inspection sketch, which will be made by outside and you can attach in the system, and then the task like visual inspection, direct thickness, and some other code which is applicable for this pipeline with other information.
Arshad, we leave it here because there is a we need to take question and answer.
Okay, so this
And
we finish.
more details are there in 5-10 minutes that could only be shown.
Yes.
But if any client or any engineer is interested in more details regarding well plant software, so we would be available. So some questions, if there are more, we can answer and then conclude the session today.
Okay, one question. How and on what basis TMLs were decided for pipelines to enter the data in the software?
See, in the pipeline side, concept of TML, CML is not there because the pipeline is in kilometers and the data is based on the KPs. And the inspection could be ILI, which is inspecting every millimeter of the pipeline, or there could be a DCVG also, SIP surveys, which the whole pipeline is covered. And then there could be bell holes for specific verifications.
Next question. PIMS software compute the remaining useful life by using which algorithm? Is it customized of any specific algorithm?
See, it is a very straightforward. The concept of remnant life is followed by API 570 is a piping one. Same can be applied in the pipeline, like a minimum required thickness, minimum measured thickness, and the difference gives us the future cooling allowance, and whatever the trend of the cooling rate is, that will help us to determine the future life of the pipeline.
Next question. Can we mix FFS software with the system?
See, FFS is there are various chapters are there. If you see API 579 is a very thick standard, and we have a separate standalone API 579 based FFS software, but it's difficult to mix with PIMS software. Otherwise, system would be very slow.
Next question. Does this inspection or analysis done on a non-metallic pipes as well? If not, how can that be evaluated?
No, you can follow the same approach for the non-metallic pipelines as well, but the equations would be a little bit different.
Next question. How to access the integrity of the pipeline after thickness erosion due to C&I issue?
See,
C&I.
no, see, ECDA, ICDA, SCCDA, those are the three mechanisms which are applied as per the NACE practice to determine if any damage mechanism is there and how that should be assessed and how that should be prevented or mitigated. So that is the approach available, and our software is following the similar standard approach.
Next question. What is the standard for isolation valve availability for cross-country pipelines to isolate a section? An example, after how many meters isolation valve should be given? Any standard or etc.?
Generally, this standard is driven by ASME B31.8 or 31.8 or 31.4. And generally it goes by 20 kilometer, 25 kilometer if you wish to. But generally those are not installed because it becomes difficult to install so many valves.
Next question. Which heat treatment methods may be used for resistance of inside and outside corrosion?
So the heat treatment, huh?
Heat.
There's no heat treatment method, there is a chemical treatment methods, right? So we covered all the questions. So thank you very much everyone for attending this session. And I hope the information was useful. And if there's more questions, please don't hesitate to contact us. And we say you bye-bye till next webinar. Thank you.